Hey, Savannah, good to see you here. We got two questions to start, it looks like. We've got the annual compensation, and then I got messaged one. Let's see, I need to find that one I was messaged, then we can do the annual compensation. Good to see you here. How's your day going, Savannah? Let's see. Here we go. The store believes. Grocery stores receipts. Okay. So what is going to be the key to all of these questions, Savannah? What is the key to every one of these questions? We gotta remember the key to doing them all. What is the key?
Notation, brother.
What is the key? Grocery stores. Receipts. The key is notation. So check it out. So the key to every problem right now is notation. It's all about notation. So these problems right here seem pretty tough till we start narrowing down the notation. So what is any of the notation on this problem? A grocery store believes that their Sunday purchases are skewed. So that's the shape of the distribution. So we've got a skewed distribution with a mean of this, the standard deviation of this. Suppose they had 301 customers. So we need notation here. We need the notation. What is any of the notation on this problem? For 100 points, any notation. This right here is also a big thing. Any notation. If you're watching this problem in the future, this is the key to these problems, is the notation. If we get the notation, we can usually solve the rest of the problem. What do you think, Savannah? Any of these jump out to you as notation? We're covering notation yesterday, and the thing is, once we get the notation, we can usually solve these problems, because on our formula sheet we have mu y bar equals mu, and standard deviation of y bar equals the original population standard deviation over the square root of n. So all this is going to be very important. Kelsey, good to see you here. We're working on this problem. Do you know any of the notation? We're going to throw 100 points right here just for people being here. What is any of the notation? Because that's going to be the key to these problems. The key to these problems is the notation. So what is any of the notation right here? So mu is true mean. Sigma is true standard deviation of a population. Both those are population mean and population standard deviation for all the data. This is sample size. This is the expected sample mean and the variation in the expected sample mean. And then which mean is that, Kelsey? Good answer, Kelsey, 100 points. Specifically, is it mu y bar? Is it y bar? Is it mu? So which one of those is that value? So very specifically, which one is it? Great job, Kelsey, right there. Which one is it very specifically? Don't worry about getting it wrong. This is the practice. So which one is it very specifically? Close. So, well, mu bar, we don't have mu bar. We have, so it's just mu. This is just mu, which that is what mu y bar is equal to. The expected sample mean is the true mean. So this is to say, if the truth is $33, we would expect to see that in a sample. So the way it works, it might sound a little confusing, is that like if the average guy at UT is 70 inches tall and you go out and talk to 10 guys, what sample mean would you expect? So it's the expected, that's why we put the mu right here before it, expected sample mean. So what sample mean would you expect? You would expect to see the true mean. So that's the expected sample mean. And so it's conceptually like if you took a sample, I think that's what a lot of people don't understand about these problems. It's like if you took a sample, what would you expect to see in that sample? We'd expect to see the true mean. That's the most likely thing to see, which is the center of the distribution when we draw it down here. So the center of the distribution is going to be right here at mu, and then we need to find out the standard deviation, which is right here. And technically this is mu y bar, but it is also mu also right there. So with this, let's go right here. And so the problem, we haven't figured that out yet. We've got here standard deviation is sigma. This is n, and this one's a little bit interesting. This is actually the sum of all the observations. So what we'd want to find out is an average. So if 10,400 is the sum, how could we figure out the average we would need from 301 customers? Well, we could take and divide this by 301. because the sum of all the y's over the sample size is equal to the mean. So the mean of the y variable. And this is the sum of all the y observations. Estimate the probability the storage revenue is at least this, and that is the sum of all the observations. So it's like if the total of all the men's height was 700 inches and we talked to 10 guys, then the average guy would be 70 inches tall. We don't usually add heights together, but this would be the sum of all the heights if we did it with a heights example. So that's just the sum of all the y observations, and this is the average of the y observations right here. So on average, we would need to see 34, there it is. That's the average right there we would need to see. If you notice, it's kind of close to the mean, but we would need to see at least this much to have at least this much total. On average, we'd see this much. So now we can go through and solve the rest of these formulas. This is equal to 33. And the original standard deviation is 22. And this is the new standard deviation for the distribution of the sample mean. There we go. And so now we have the mean and the standard deviation, and it's time to bring it over to the apps. So with this question now, we could draw it out here on the bottom. All the apps really does for us is draw the distribution. This is going to be about 1.28 standard deviations. So the answer is going to be close to, so it says 4 decimals, which is very, very hard to guess. Like probability of me getting this right on a guess is super duper low. This one I have no idea yet, so I'm just going to enter 1 for the time being. But that's going to be a decent guess on the first one. We'll see how close we are when we go to the apps right here. On the test, we might have you do like a z-score for this. The z-score for this is going to be a little bit more than 1. So here's something you could do on the test technically, is you could take the y observed value right here. Let's go show like as a test question how this could look. It's a good say, find the z, really? Wow. Oh my gosh, this computer possessed? What in the world? I click this and it changes it back. Oh my gosh, what is, okay. Now it's not responding. Doesn't want to do it. Oh my gosh, what have we done? There we go. Oh, this is not good. What's going on here? Okay. That was weird. Okay. So we have here y. Really? Oh, what the heck is going on with Word? Well, y bar minus mu over sigma over square root of n. And that is equal to 3 point, oh, got to grab the numbers from the other one. Don't know what's going on with that. 3.45. Can we do it over here? No. 34.55 over, let's see around here, and 1.268. And this is going to give us a z-score right here. So this is the formula for a z-score. And this is going to give us 1.2222, and that can be used to find the answer now. But that's what we could ask you for on the test is the z-score. So it's not that unusual, and 1.2816. So yeah, it's a little bit more than 10% since I know some of the numbers on the curve. But we're going to go right here and enter in the mean of 33, I think it was. Let's find the mean again. The mean is 33. The standard deviation is 1.268. I would carry all your decimals. So when you're doing this problem right here, I do highly suggest to be over here and do 301 square root, 22 divided by that, and then just drop this number over here with all the decimals. Do not round till the final answer. Now we need to find above a certain value, and that value was, let's go put all the decimals in for this value, this 34.55, and that was 10,400 divided by 301, and we're going to drop this in with all the decimals too, and so we're going above this value right here, and as I said, it's about 11%, and then we can go ahead and round it to 4 decimals, so 11.06. So my guess was kind of close. There was my guess. And there's the actual answer to that problem. So pretty good problem right there, and understanding how we could find the z-score by ourselves. And if you use the z-score, you would get the same answer too, going above that z-score. But make sure to carry all your decimals till the end, since it is 4 decimal place accuracy. Now it wants to know the best 1% of days. What's really great is, since we have everything already set up on the app right here with all of our decimals, we can go back here to where we find a value of x using the probability, which is kind of the p-value. We're going to go here to the top 1%, which is all the way over here on the right side of the curve. Now, this is how much they would make on average from each customer, and we had 301 customers. So there is how much they would make. So I just multiplied, if you can't see it right there, I multiplied it by 301 to get the value. So this is how much they would make in total. And we go back here and bring this in and drop it to 2 decimals. And there's the value right there. We should, 50%? What did it say? 2 decimals. Well, you got to be kidding me. This one should be right. Check. Okay, this one's not correct. Uh-oh. Look at this. The worst 1%, not the best. So now we need to go over here to the below. Went too quick on that one. The worst 1%. So now we need to multiply the worst 1%. And there we go. So I was like, what did we do wrong? I thought it said the best, but it was the worst. So be very careful. The worst is going to be on the left side of the curve, and the best is going to be on the right side of the curve. I thought it said best. Never read the questions too quickly, because that is the worst 1%. Not the best 1%, and the worst 1% would be the lower 1% on the curve, and that's going to be on average of this per customer. Since we did have 301 customers, we're going to multiply that value by 301 to find how much we make in total. So really good question right here. It's like the waiter waitress question, just a different context of it. But understanding how to mark your notation is the key to these problems. So you need to mark all the notation, draw the curve, find the sample mean, and on the test, we really couldn't have you. We could ask the lowest 2.5%. That is obtainable, and we could say estimate it, because the lowest 2.5% would be 2 standard deviations below the mean. So if you were to find that, hypothetically, and this is another way we could do the test. Oh, you gonna let me draw on this? Okay, it might. No, this one's possessed. We could ask you to go here and go 2 standard deviations below. Now, the common mistake is a lot of people don't use the new standard deviation. The new standard deviation of the curve is 1.268. So they would need to go down minus 1.27, minus 1.27. And this would be the worst 2.5% of days right here. So if we go down considerably 2 standard deviations, so 33 minus 1.27, and then we do it again, 30.46. And then we could times this by 301. Yep, we can go in here next, Savannah, you got it. So we can take this value, times it by 301, and that's the worst 2.5% of days. And just to show you, if you watch that answer right there, the worst 2.5% of days, we could do with the applet too. And so here's the answer I currently have. We'll just kind of store this as a screenshot to show this is what we got without the applet. So there's our without the applet answer right there. And here's the answer with the applet, 30.515. We'll do that right there, times 301. And there's the answer with the applet. So very close answers, what you could get without the applet. So there is with the applet and without the applet. Similar ask answers. The applet just does a more exact answer for you to get more decimal place accuracy. It's within a couple $17 or so. So really good question, good practice right there. And once again, we could solve this out without the applet to do the worst 2.5% of days. The worst 1% of days does not land on an empirical rule number. So the worst 1% of days we have to use the applet for. Here, let's do the CEO question. I think this one right here. Can we do the, shows the annual compensation in thousands? Is it this one right here? The histogram. There's a different one that says the histogram. Here it is right here. The histogram shows the annual compensation of CEOs in thousands of dollars. Okay, let's do this one. The histogram shows. Okay, the histogram to the right shows the annual compensation in thousands of dollars of the chief executive officers, CEOs of 800 large companies. So the first thing we have to do right here, Savannah, is what? What is the first thing we have to do? The very first thing we have to do for this is what? It is skewed to the left. Great job right there. And so what do we have to do? Great job. 100 points right there. What do we have to do with this question now? First thing we have to do is what? What do we have to do first? There's a lot of steps. Now, there's a lot of what we could do first. So what are some good ideas for this question to solve it? So the goal is to learn how to solve these problems. It's not about solving the problems, it's learning how to solve them and having a pathway when you get to the test to be like, oh, I know what to do for this problem. So it's not about the answer to the problem, it's about how do we solve it each time we get to a new problem. So what are some things we should do first here? Got two good ideas. What are one of the two things we could do when we get to this problem? There's two big things we could do to help ourselves out. Give it a moment more here. What are one of the two things we could do? So if you're watching this in the future, try to remember that one of the two things I say we should do when we start these problems that are going to give us a huge help and help us get the right answers on the test, because we're focusing on doing well on the test. So what could we do right now? And I don't know is a fine answer. Don't worry if it's I don't know. So what can we do? Any thoughts? What is the way to solve this problem? So once again, we're not even looking at the questions yet. Don't worry about the questions yet, because we should understand what we're doing right here. Another 30 seconds. What could we do? What are your thoughts? Big things right here. Someone might have skipped ahead to be like, okay, how do we solve this? No. You gotta think about how do we solve this? That's the key to solving these in the future. It's not about solving this one problem, it's knowing how to solve it on the test. What do you think? There's the bell. The answer is
notation, brother.
It's all about that notation. One of the first things we can do too is we can figure out if it's quantitative or categorical. So this is average compensation rate, which is quantitative. So we're dealing with a quantitative variable. So I would know it's quantitative. Then we have these right here. So Savannah, what is any of the notation here? What is any of the notation? Help me out here. Here, we'll pause again. What is any of the notation? And so we're trying to find things like mu y bar equals mu, and standard deviation y bar equals sigma over square root of n. So what is any of the notation here? Like, what are any of the things on the screen currently? What are they? So what do you think they are? Anything on the screen right there, what is it? Interestingly enough, this is something too which we won't use. Let's look at another 30 seconds right here. Practice makes perfect. The more you attempt it, the better you get at it. So if you're watching this in the future right now, try to mark the notation right here and know what each thing is. You have to be very specific. So mu is the true mean, y bar is the sample mean, mu y bar is the expected sample mean, SD y bar is the variation in the sample mean, sigma is the true standard deviation, and n is the sample size. Capital N is the population size. Oh, there's the bell right there. Okay. So what we have right here is this is the true mean, which because that's for everybody, the full population size. That's the population size right there. These are different sample sizes they will use, and this is the standard deviation. So that gives us what we need to plug in to solve the problem. So with this, we know the notation for the problem, and let's see what they're asking for this. Describe it right here. It is skewed to the left, so we know that one. Explain how these histograms and simulated samples demonstrate the central limit theorem. Well, the central limit theorem says two things. One, that the distribution will become more normal, and two, that it'll become tighter. So let's see this in action. So the sampling distribution applet is a great way to see this. When you look at the distribution of the original data, which they're showing you currently, it was skewed to the left. So we could draw this distribution right here and draw a skewed left distribution like they have. So this is their skewed left distribution. Now, for a small sample size of 2, this is the distribution of sample means of size 2, as in every blue dot is a mean of 2 observations up above. And that's usually where people kind of are confused with what we're doing with this chapter, is we're not talking about the distribution of the individuals' compensations, the CEOs' individuals' compensations. We're talking about the average of multiple CEOs and the distribution of those averages. So if you do this repeatedly, you'll notice this is still left skewed, but as you increase N, it starts to get more normal. And check this out, we are now averaging 25 random CEOs, which is less than 10% of the total population. And then we get one blue dot here, which is the average of 25. So this is the distribution of sample means of size 25, and it is still left skewed. You can still see it over here, the left skew on it, because this was a stronger left skew. But as we increase the size of the sample, like 5 right here, then this distribution is less skewed and tighter. And that's the two things that the central limit theorem says, is that the distribution will become less skewed and tighter, and you can see it, sample size of 30, 50, 100, and 200, and it becomes less skewed and tighter. Notice how it only goes from here to here. Really, there's a little bit down there, but for the sample size of 30, it's from here to here. And the number line, I think, has remained the same, so it's easy to tell that it's less skewed. It's tighter, and it's more normal. Also, it starts to build up that peak. Now, here's the interesting thing. So the simulations support what the central limit theorem says. It's a theorem. The peak of the histogram stays about the same, and that's also one of the formulas we have, where we have talked about repeatedly mu y bar equals mu. So the true mean is where the sample mean is expected to be. That's expected sample mean. So that's the first thing they're saying. And then the standard deviation of y bar will get smaller by a factor of square root of n. So that's kind of key right there. So there's the shape becomes more normal, one of the things the central limit theorem says, and the variability, which is the standard deviation, is going to decrease. Once again, understand that we're talking about these two formulas right here, that the mean of the sampling distribution is the mean, and the standard deviation decreases as n increases. And then also we can see it becomes more normal. The shape becomes more normal right here, and the tighter is the smaller standard deviation. So very, very important right there, understanding those concepts. Now, this is what's interesting, is they're saying that there's a rule of thumb of at least 30. There is no rule of thumb of at least 30. The condition here is called what? What is the third condition? So this is a big pause moment. If you're in my class, you know what I'm talking about. What is the third condition for the distribution of the sample mean? What is the third condition? Third condition for the distribution of the sample mean. So Savannah, it's a really good question right here. What is the third condition for the distribution of the sample mean? What is the third condition for the distribution of the sample mean? What is the third condition for the distribution of the sample mean? What is the third condition? So you'll give it 30 seconds. So the reason I'm pausing here is a lot of people get this condition wrong. And so what is the third condition for the distribution of the sample mean? I didn't even go take a screenshot. While we're doing this right here, let me take a screenshot from previous office hours because I have it written down so well. Make Chrome faster. What is the third condition for the distribution of the sample mean? There's the bell right there. Where did I put it? Oh, there it is. Disappear off the screen? No. On the screen. Oh, there we go. I want there not to be writing on this. Oh, there we go. The third condition for the distribution of the sample mean is the large enough n condition. I guess I gotta write this out some of that time. Oh, no worries. 100 points right there. So it's the large enough n condition. the large enough n condition. So when it's quantitative, it's the large enough n. And that's why I pause on this, because a lot of people just go success failure because it's the first one we learned. So the thing is when we do quantitative data, remember, we pause before the third condition, and the third condition with quantitative data will be the large enough n condition. So the way we check this is we look at the shape of the distribution. So the shape of this distribution is very skewed. So then since it's very skewed, we say what size is required. Now we usually do 125, 100, but you could have like very, very skewed. So is the rule of thumb that 30 is always good? No, there's no rule of thumb that 30 is always good. It really depends on the shape of the distribution. Since the distribution of the means for the simulated samples become more normal, so neither of these, they don't become less normal, they do become less skewed. The rule of thumb doesn't hold though, because it's not 30 as a rule of thumb. Since the distribution of the means for the simulated samples of each size, nope. Here we go. Since the distribution of means for the simulated samples of any size remains skewed, do you see how they remain skewed right here? They're becoming more normal, but they remain skewed. The rule of thumb does not hold for highly skewed distributions. And what you need is, for highly skewed distributions, you need a what? The more skewed it is, and this is what the rule is, you need a what or what? So the more skewed it is, you need a what or what? So the more skewed the data is, hey, what's up, Jesse? Need a what? The more skewed the data is, you need a what or what? We're done with, we got open time for questions, so feel free to ask any questions. So remember, the more skewed the quantitative data is, we need a what or what? Larger sample. Great job, Jesse, right there. Yep. We need a larger n, which is the sample size. Exactly. So the more skewed the data is, the larger the n we need. And that should do it. Good question right there. Once again, it's multiple choice, so you have to understand the concepts behind it. But yeah, so which one should we do right now? I don't know. We've only got a few more. We've done a lot of these already. I'm trying to think of ones we haven't done yet, because we've done like all these. We didn't do the waist size one yet. A study measured the waist size. So let's do that one. A study measured the waist size. Okay, let's check it out. Stat Tool 1, Chapter 14. A study measured the waist size. Okay. Here we go. Let's check it out. First thing we always do with any of these problems is what? What do we do? First thing you should know by now, that's the practice we do to make perfect. Anytime we get a question like this, we're always going to do what with them? We're always going to do what? Always going to do what? Anytime we do this, we're going to do what? Good practice right here. So if you're watching this in the future, you should think, okay, I need to what now? And these are tougher because they give you a lot of numbers. First thing we do is notation. Kelsey knows. Does anyone know any of the notation? There's a lot of numbers on the screen. We'll be solving for like mu y bar equals mu. Standard deviation y bar equals sigma over square root of n. And this is because waist size is a quantitative variable. So what is any of the notation here? This is tough because you would think some of the things are something else. Like I could see how someone could get very confused on this problem quickly because it gives you a lot of numbers. So we have to be very specific on what each thing is. And part B kind of makes something a little bit clearer. Let's see. We'll give it just a moment longer. See if you can mark the notation. So if you're watching this in the future, once again, I keep saying that, but this is where the practice comes in to where you get yourself ready for the test. It's not about solving this one problem. It's about knowing how to do problems like this. And when you get to the notation to be like, okay, waist size, think about if you ask someone their waist size, like the way to know if a variable is quantitative or categorical is to say, how big is your waist? And I say, oh, 33 inches. And so that then is a quantitative measurement. Or you could say, like, do you wear small, medium, or large clothing? And I could say medium clothing. That's a category right there. So you have to think, like what percent of when men wear medium shirts? That would be categorical. Then if you think, what is the waist size of men, or what's the average waist size of 10 men? That's quantitative, because waist size is a number where shirt is a category of small, medium, large. So you have to ask the question to yourself, like, what percent of people wear medium shirts? Do you wear a medium shirt? Categorical. What percent of men have a waist? If we were to take 10 men, what's the probability they'd have a waist size above 34? Quantitative, because when we ask people what's their waist size, that's quantitative. So this is quantitative right here. So these would be the formulas you would look at on the formula sheet. So the notation right here, these are the different sample sizes, and this is the population they're drawing from. I think that's usually where people get a little bit confused. It does say a study, but they're going to sample from this, and that makes it the population. Yeah, great job right there. And then Kelsey's right. Kelsey, 100 points. This is sigma right here, true standard deviation. This is mu, true mean. And now we can plug them in. And so this is equal to 3.92. And then it might have us like solve different one. There's a lot of problems that have you resolve for the new standard deviation. And look at that. I already made a mistake. I'm already making errors. This is mu. That's sigma. I was like, think about it, the average waist size of a guy is not 3.92 inches. So it's 36.37? Sure. Yeah, I guess. I don't know. 3.92, and then we'll do it over different ends right here, which will lead to different standard deviations. And as you can see, if you plug in these different ends, as n increases, the distribution will get tighter. And that, once again, is one of the concepts of the central limit theorem, that the distribution of sample means of larger sample sizes will get tighter. And once again, it means that if we took 25 random guys, so this is the distribution of sample means of sample size 25, we would find the average of 25 random guys, and we could repeatedly do this process to see what the distribution of sample means of sample size of 25 would look like. So I just want to clarify this a lot, because we only have this question right now. So hopefully this helps people understand these concepts. Hey, Blake, 100 points. I haven't seen you for a while. People are getting to your level right here. So, I don't want to download the new R. Don't want to download the new R. Just want R to download, or just want R to open up. Let me do don't update. Remind me later. Ignore. I should hit ignore update. Okay. So what we have going on right here is it says that the mean of men's waists is about 37. The standard deviation is about something like 3. So we are going to, and it could be normally distributed. We're going to take from the random normal. We're going to take, let's say, 10 men, where the mean is equal to the mean, and standard deviation. So these are the waists of 10 men. So here we go. Let's go here to waists. Those are the waists. I can't say weights. Waists. I can't say it today. Of 10 men. You can see here that's the man with the biggest waist. Then we have some men with smaller waists. And then what we would do is we would take the mean of this. There's the mean of it. If you notice, it's kind of close to 37 each time. It might be a little bit above or below. But now I'm repeating the process with 10 different men. If you notice this time when I simulate it, we get 10 different men. And this is what you're seeing in the applet right here when we go here and draw 10 random men, and then we find the mean of it, so mean of them. So these are the 10 random men we're drawing, and there's the mean. So this is the drawing of 10 random men and measuring their waists. So there's their waist size of 10 random men, and here's the mean of the 10 random men. Now what happens is we repeatedly do this process. Now we could store this here as, let's go here, we'll just do this as output here, and then we could go to 4, and we could simulate this process 10,000 times. And so now we put this here, and this is not what you'd be doing in Stat 201, but we can simulate this process right here for the output and do a histogram of the output. So this, ooh, what's going on there? Ooh, what did I do? So something broke, something didn't do. For I in 1 through 10,000, what did I do? 2 seconds. All those NAs. Store right here. Oh my gosh. Why did I do that? There we go. Forgot to put the vector. There we go. This is the histogram of the sample size of 10 versus if we were to just do a histogram of a bunch of observations from this data. Here's the original histogram with more variation, and here's the new histogram. Look at the number line, it's much tighter. And if I increase the sample size right here to where we're sampling, let's say 100 men, what you'll notice is the histogram gets even tighter. So as I increase this to where we'd be taking tons and tons of men, it becomes tighter and tighter and tighter compared to the original data right here, which has a much greater span. Like, it's possible for one man to have a waist of 25 or one man to have a waist of 50. But if you were to average together 100 men, well, the average of 100 men would be a much tighter distribution because each little height of the bin right here is populated by the average of 100 men. So that's got it right there. That's a much more in-depth explanation of this problem and the theory behind it. So let's see right here, describe the histogram of waist sizes. Well, the original histogram has a left skew to it. These simulations right here are going to show that it becomes normal. And if you look, and this is going to be the tough part, if they're asking when it becomes normal, it might around 10. I think 10 is good enough. So we're saying probably when does it meet the nearly normal large enough n? So these simulations appear to show all of the histograms are centered around this. That's because the mean is equal to the mean. And so they're centered around 36 because the mean doesn't change. The standard deviation will get smaller as n increases. As n gets larger, the histograms become more normal, approach to normal shape, and the variability in the sample means decreases. The histograms, and here we go, are fairly normal by the sample size reaching 5. So it's kind of normal. I thought around 10, but they're going a little more here. And I think they used to have you input the 5 number, but maybe they saw that people were not getting that right. But they're fairly normal, which is what we're going with. So pretty good question. But the theory is what's most important about this is that the central limit theorem states that the distribution of the sample means will be tighter and more normal. So if you do have skewed data right here, as you increase n, the distribution is going to become more normal. And you can see it right there, the distribution becoming more normal and tighter. The two things that the central limit theorem says. Okay, let's do another question right here. Let's see, question 7. Well, we've done this one. We've done so many of these questions. I think have we done all of them? There's not that many for this chapter. And these are the tougher chapters right here. We did the waiter waitress one. Did we do questions 1 and 2? This one's tough. Has a lot of parts. We did the food company. What are people thinking? This is a tougher chapter, but I think we've done all of them now. Just wondering if I should do some 320 now. Maybe I'll message 320 and say, like, covering a little 320. We'll see if Sat1 has more questions. Let me say at BS320. Talking over this week's assignment in office hours. Swing by. Okay, here we go. We'll message out to them and we'll see what people say. So we'll put a call out. Make Chrome faster. There we go. All right. So let's talk over this week's assignment for 320. I know haircut Brian, right? Short hair Brian for the moment. Glasses Brian, short hair Brian, Wacky Wednesday Brian. Do a little Wacky Wednesday and mark the notes right here. Oh, crap. Okay, we got the weekly assignment right here. And let's talk about some 320. So it's really great if you're in 201 right now, if you're watching this, we're actually doing multiple regression in 320. And so you've learned regression in 201, but multiple regression is just using multiple x's. So we're going to load in the MT-cars data, and that should load in the global environment now. Let's see right here, do we get the MT-cars data? There's the MT-cars data. Promise means it promises to me that it's there. And this is data on a bunch of cars, the miles per gallon they get, the cylinders they have, the displacement, which is like a ratio. Nice job, Sloan, right there. Yeah, the notation. If you know the notation, you get it right. We've got V versus straight line for engine. So that's actually categorical right there. We've got different things like the weight of a car. And what's really great about R is if you go right here and do a question mark on this, I didn't do a question mark. So question mark MT cars. It's actually going to tell you about the Motor Trend car road test right here and tell you the different variables. Know your notation.
Notation, brother.
We've been using that a lot today. So these are the different variables you see in there. We can also load in a library. I do suggest using things like this to use Glimpse. And Glimpse right here is going to give us a glimpse of the data set, and it populates to the screen. So you can kind of see what's going on with the data set right there. Now, here's the thing. To make a regression in R, we just do, we save into the object M, we type LM for linear model, and we say, let's look at the miles per gallon of a car explained by the horsepower. And it got mad at me because I didn't put the data set it's in. So I have to tell it it's in the empty cars data frame right here. That's where the variables exist. So I have to say y tilde x. That's just a formula right there. And that's the first argument, like the first set of instructions. Make a regression using this. And data equals MT cars. So now let's go here and summarize it. And this is a summary of the model. And what's really interesting is this is just like jump output, where you see right here the estimate of the intercept, the estimate of the slope, the standard error, which is our level of uncertainty in the estimate of the intercept, the standard error of the slope, which is our uncertainty in the slope, the t ratio right there, also known as a t value, is the ratio of these two numbers. So you can see it right there. And the p-value is the probability of getting a t-value this extreme or more extreme, hence why it says probability greater than absolute value of t. So it's actually finding it for it on the applets of sorts, which we were doing the applets earlier. Down here, we have the significant codes to tell us the p-values are statistically significant, that they're basically 0. It's between 0 to 0.0001, but these are very, very small p-values. Good to see you, Trenton. We have the residual standard error, which is the typical miss the model makes. When the model predicts miles per gallon, it's typically off by about 3.863. The 30 degrees of freedom is used to calculate. That's not so important. The multiple R squared, it means 60.24% of the variation in miles per gallon is explained by horsepower of a car. The adjusted R squared is how much we explain after we kind of penalize ourselves for the variables in the model. So it's adjusted for how many variables in the model. The F statistic is a ratio of what we observe being explained versus what we expect versus random chance. Not super important, and this is used to calculate also. And the p-value of the model is the p-value of the x variable because the x variable is the model right here. And so with this right here, we can make it a multiple regression really easily by just adding in something like weight. And now we have two variables in the model. And the most important variable in the model for explaining miles per gallon is the weight of a car. So the weight of a car is going to be the most significant variable. We don't really care about the intercept because the intercept is just an arbitrary point. But at this point right here, and let me see something. I'm going to check some stuff out for lab kind of in advance right here. But I wonder if, let's see right here. Graphing multiple regression in R. Let's see. Oh, they're literally using the same data set. And we got ads over there. So let's, oh, yeah. Can we not show the ads? They're going to say, you got to see those ads over there. They're using same data set, which is nice right here. And they're doing like different plots. I don't love it. Huh. Let's try this. Do I have that? Interesting. Interesting. But what if we have... So it does do multiple plots. It's using the row names. Is the P50? No, it's not. I don't think it is. So I don't love these plots because I don't think they're the most informative. So let me see. That's from 2020. Here's GG Predict. Visualize multiple regression model. That's I've done that. I think an interaction right there. Ooh, that's nice. Is it just GG Predict? What function, what package is this in? Do I have GG Predict? Okay, here we go. There it is right there. Let's take a look at this. Okay, do I have these? I might need to install these if I don't have them. Nope. Nope. Oh, I do have that last one. Okay, so installed packages. There we go. Nope. Go installing that one. Looks like it did it. There we go. GG RF extra. There we go. Okay. And could not find function GG predict. So where is that GG predict? In the, it says it's in the GG IRF extra packages. So GG IRF extra. Did I get that or did it fail to download? GG IRF extra. There it is. Make interactive GG plus extension for that right there. No, it's saying failed to load. Okay. So let's try reloading R real quick and see if it got mad at me. Hopefully it's not like I need to update R. Ignore update. There we go. Oh, it's failing to load those. That's not good. Oh, it's saying vectors is required. It's saying it requires an update to vectors. So what we need to do is we need to go here to vectors. And this is the one that is the problem. And it's saying this is not happy. So here we'll do this. We'll remove that. It's probably a horrible idea. And then we'll go install.packages, vectors. Oops. And nope. Okay, so maybe it's good now. Uh-oh. Might not have it. Okay, it doesn't look good. It looks like it doesn't like it. Sure, restart R. And I might have to go into R to do this. Uh-oh. I'm getting all this stuff. Nope. Okay, wait. Okay, installed successfully. 0.61. There we go. And so now, okay, rlang. Rlang is the problem now too? rlang, what? But really? So now we gotta, oh my gosh. This is the fun of updating software. Restart. Sometimes you gotta fix things. There we go. We got the latest 1.1. There we go. Up. Good. Up. Good. We're good. Warnings that it was created using a higher version, I think, than RR, which is not the end of the world. But we had things that were not compatible. So that's what we were trying to fix up right there. So getting all that fixed up should have us being able to use this. So all those are loaded in, empty cars data, take a look at the data, bring in the data right there. And we don't need this anymore. The fit, I usually store to M. Some people call it fit. I like to call it model. And let's see what this looks like. All that work. And I'm not loving it. Not loving it. Ooh, changes the whole plot window right there. Interesting. Let's remove out the cylinders from it. Hmm. So it's decent, and it's a GG plot, so we should be able to add like here GG title or labs. And with labs, we should be able to go title equals my title. And oh, it's mad about that? Next method. So the GG predict, that should be a GG plot right there. I would think it is. Oh, it's a plotly. It's, well, oh no. Oh, I think it is a plotly. Interesting. So we can export this image here. And let's look at the GG predict function right here. All this work to get this, and I'm thinking it's okay. Fit color and color size, color and color that many. Point jitter, show summary, color as factor, digits interactive. We put interactive true. Okay. Now will it? No, it doesn't like could not find function in labs. Oh, ggplot. It's not turned on. There we go. We did get the title with the interactive. Good to see you too. Thank you very much for being here, Blake. We're just checking this out right now and seeing what we can do with it. I mean, it's a pretty good plot. Shows you kind of how the predicted model changes for weight right there. That weight is going to, for if you look here, higher weights is going to have lower. So weight has to have a negative coefficient. You can see here the coefficient of weight is negative, and the coefficient of miles of HP horsepower is negative also. How it impacts miles per gallon. So I think it's a little bit better. I think where we get into the problem here is when we start adding in more variables. When we start adding in 3 variables, that's where I get a little bit concerned, because here we'll add in disp for displacement. That's where it's going to start to look very cumbersome, and I don't know how interpretive we could really get with it. So now this is a 3 variable. It looks like it's getting a little bit mad right there, and it's making different plots. So it's actually using, I think, the facet grid, and this is where I would not use it, because it's very hard oftentimes to visualize multiple regressions, and that's the problem we run into. Yeah, I know, right, Jesse? So probably this is going to be our best visualization right here, showing that at higher weights, the lower predicted miles per gallon. It's also doing a color on it right there. But once again, the coefficients are leading us to know that there is a negative relationship with weight and horsepower to predict the miles per gallon of a car. As in, the cars that would get the highest predictions would be the ones with the lightest weight. You see the dark colors up there, and the lowest horsepower. So these cars over here obviously are predicted. And you want the lines to be kind of near the points. So this is pretty good right here. And we can add all the titles. We can change the X title to. So X equals horsepower. I think it's one word right there. So that's a lot better. And then this is what we try to focus on in our class. Is we want the plots to look really good. So this is what we really focus on, is like, okay, we're going to make sure that we have a good looking plot right here. And we could call this predicting miles per gallon. And there we go with a pretty good plot pretty quickly. And this is what we want it to look like. We want it to look nice. Let's go ahead and before we throw the labs on, let's go here to GG themes and go here to GG themes. And inside of GG themes, it helps if I can see them. Theme what? Theme. Let's go to 538 and see what that looks like. Well, there's that. We don't like that. I don't think that's going to work. Nope. So we're just looking at the different themes for a moment. And there's so many different themes here. Theme. I think this one I've used a lot. Yeah, not bad. But the themes are just like presets that you can use to make it look different. So you can get different looks for your graphs. They also have like Excel themes. So you can go to the Excel theme right there and make it look like Excel, or the new Excel, which I guess is the newer version of Excel right there. But it will kind of mimic what you would get from those outputs. So it depends on how you want your graph to look. But you can change anything on here, but all these themes are going to be nice and easy, and we just added on the theme. So it's really about make your graph look nice, make it look understandable to your audience, and then of course you can export the image right here, save the image right here, and get a nice clean shot of it. So I don't like how that's a little bit blurry. So a lot of times I will go inside of here and I will screenshot my own image so I can just get it the way I want it. But one thing I want to point out is when you have this image the way you want it, and you bring it over to your Word document, what you don't want to do is you don't want to start doing this. You don't want to grab on any of the corners like that. That'll kind of squish the image. You want to grab on the corner, and I did say corner, but that's where you do want to grab. You don't want to grab on one of the sides here between. The corner keeps the aspect ratio. So if you didn't like the aspect ratio originally of your image, you could go right here and change it, and it'll actually re-update the image. So if you did want something a little bit longer for your output, you could go right here and get it looking like this. And this is going to be a much better way. We'll take a nice clean screenshot here. This is going to be a much better way right here. Instead of taking your image, and there's that image, if you were to try to replicate this right here and be like, okay, I'm going to squish it and make it look like this, you see it looks very stretched out. So you don't want to do that with your image. You want to get the aspect ratio you want in the picture. You don't want to change it up here after you've taken the screenshot. So just little small things like that are going to make your report look a lot better, to where you get the image the way you want it, put it into your report, and get a good clean screenshot, rather than saying, let me get this image to be the way I want it here, and then all of a sudden it looks like that and you can't read it. So get your image the way you want it, and then only change it via the aspect ratio that keeps the aspect ratio. So the corner right there, very, very important right there. Center it. You can even go here, last few things. I like to add maybe a border, or you don't use that. There's lots of things you can add to this. Like some people use that. Not the end of the world if you use that. That's good. I think that's one of your best ones. This is decent. And then a nice border around it too might work. But that kind of makes it pop a little bit from the page, gives a little bit of depth. There's lots of options, though. I would be careful. I wouldn't do crazy things like this that are going to destroy the ability to see your image. Or don't go 3D. That looks like a Nintendo Wii. It's not the worst. I wouldn't. It's a little bit weird. It's so interesting. All these little things you can do that just make things pop a little bit more from the page. Just give it a little bit of a border. You can also go right here and change the border sizes. Not too bad right there. It's got a little bit of a shadow around it. I don't know. Depends on what you like. Depends on what your company likes. If he'll come back to you and say amazing plots, you can say, yeah, here's what I did. This is how I made it look really great. Picture border. So you could just go in here and put the picture border. Oh, you see? Just doing that around it right there. Put a little border around it. And that right there. If you want to go simple, there you go. Just improved it. Just a good bit right there. But just think about all these little things you can do. Page layout, we don't want to do that. And then you could add in your own shadows if you want to go here, and you can actually change how big the shadow is. I have too much fun with this kind of stuff. So look at that. We did our own custom thing for the graphic. Company might not like that bevel though. What up, Ty? Good to see you here. So with this, we have our regression right here. But when we do regression, we want to say, is this appropriate? And do remember, we need to pull up right here, library reg class, and check regression on this is in reg class. But remember, we're not going to use these plots. I mean, you can. I'd be careful, though. I want them to look more professional than this. We do have issues here of the linearity. I can already see it, and I was right that there's linearity problems. It was just very apparent in the residual plot. So this is the QQ straight enough. No outliers plot doesn't thicken for stat 201. And so linearity is straight enough. Then we have here plot doesn't thicken, which is actually fine. The p-value is good enough. And then the no outliers is kind of by the the normality QQ plot. And there is a bit of an issue here, but truthfully, it's mostly good except for a few extreme outliers on the high side. So mostly good. Don't look at the histogram though. So remember, when we do this, we can get the residuals for the model by going right here and doing residuals of M, and we actually have all the residuals. So if we want, library ggpub_r has ways of making the GG histogram for us. And can we just do it? There we go. There's a histogram of the residuals. And is it GG normal probability plot? Oh, look at that. There is a normal quantile plot of the residuals. And actually, this one gives us the bands, which I keep looking for. Let's look at the instructions on this a little bit more. And color black. So let's change this to color conventionals. Red? Or no. I want the bands to be different, though. The band size, shape, add Q lines. So it is adding those in. Add QQ lines, and none are the options. Confidence intervals. Oh, nice. So those are the conventionals we're adding in, and the theme is GG Pub R currently. So I'm trying to see. We don't need to facet by multiple variables, so it can just take the data, which is awesome. Merge, combined, palette size. What if we do palette? Let's try this. Palette. And then we need to put a vector here of red. It needs to be lowercase, right? Red. That always gets me. Green. Let's see what this does. Blue. Okay. It's mad about that. We didn't put a comma. Okay, so it might have not used the color argument. It's mad at me over there. Okay, so that didn't do it. Did you forget to specify an aesthetic? I think it's saying we're not even using these. Darn it. We'll see if they use a palette and look at their examples here in a moment. Okay. Let's look at their examples with a palette, if they did do one with a palette, and they probably didn't. Here we go. Oh, you have to do color by a certain thing. So, yeah. Then it's going to do, okay, so we had to specify a color. Well, that's a bummer. I wanted to change the colors of the bands, and we should not. There's the code. Here's their code right here. Is it that simple? No way is it that simple. Okay. Oof, it's a big start to it. If missing ops is null, this is the weirdest code I've seen for it. GG QQ plot core. Oh, they're storing that. Oh, wow. That's man, I want to talk to Petrie about that one. That's so crazy. Let's see. Default is false. User multiple font. We don't need that. I really just want to change the bands because I don't like that the bands. It's something so simple can be so interesting to solve because I want these bands to be different colors. Everything else is easy to change. We can just change. We could grab our labs right here. We could grab the theme, do our same theme, do our same labs, and now we've got the same sort of theme on the plot. Once again, all we did was copy paste all that stuff here. We don't want to use the same title. We do want to add on our easy center title. So frankly, I should have just grabbed everything after this. And this is the good part about coding is you can get it to look very similar and get the same stuff set to this. So now we'd go right here and we would just say QQ normality plot or normal quantile plot. There's the normal quantile plot, and the X is going to be the predicted for normal, and the Y is the observed value. So you can see over here on the far side that these are higher than they are predicted to be. So they're predicted to be over here, but they're a z-score much higher. These are all z-scores right here. So observed, we could say observed z-score. If you'll know what z-scores, that would help. And predicted z-score from normal. It's predicted z-score from normal. And now we've helped out the reader maybe a little bit. Reading a normal quantile plot might be harder for people, but the observed z-score right here is higher than the predicted z-score. That's where the line is at, and it's outside what we would expect. So just a few outliers on this is the issue. It wasn't my biggest concern. My bigger concern is the bend in the model. Let's show how to look over that. So the bend in the model might be a little bit interesting this time to look over the bend, but this plot right here is pretty good. You could go to color on it, so we could throw the color back on it. Color equals blue, lowercase blue, and you get that. So that's pretty nice. Whatever you want though, and you could work around with the color codes right here to whatever you want. Is 00 technically. So whatever you like, that is the UT orange color code right there. But we got a pretty nice plot. Make sure to save it, bring it over, get a good screenshot. And this is going to be for the normality of the residuals. But what we also want, and we should be able to do this, is show the residuals versus the predicted values. So the first plot Petrie creates, let's make that again. So the first plot right here is the predicted values as the x and the residuals as the y. So what we want to do is we want to go here to, let's see right here. If we want to do ggScatter then. From our model, these are the predicted values. Let's store those onto the empty cars data frame as predicted. And now we've just stored the predicted values on. And then let's go to ggScatter. And the ggScatter takes data, x, and y. So we want the data empty cars, and then x equals, and the x is going to be the predicted value, and the y is the residual. So guess what we got to do right here? We got to go and drop our residuals over here, not with K, and go to residuals of our model, and there's the residuals. And now we're going to plot this right here. And this will be the residuals. And that should do it. There we go. So now, if you notice, we actually have made the first plot right here. This is the plot, but we're missing the line in the middle of it. So to add the line, we need to do geom. So GG, or is it GG horizontal line or geom H line? Horizontal line. There it is right there. Geom H line. So the mapping, I always have to double think about how to use these. So we're using the F1 to do the help right here. And you notice they're just showing us right here. You just add it on with geom H line, and you have to do y-intercept. So the y-intercept is going to be equal to 0. And there we go. We've added the line. You can really see the curvature going through the model. It'd be great if we could plot that, but you'll notice inside of here there is the bend, especially towards the end. The line should be at the center around all points. And once again, the nicest thing we can do right here is we can literally just grab all of this stuff we added on to the other plots. And once again, all we're doing is copying that and bringing it right here and adding it on, and we make a much nicer plot. What about I don't think it would, so that's actually the AB line. AB line uses that format right there. So thank you, Jack, right there for mentioning that. That's the format of AB line. So that's why things can get confusing. AB line does that. I don't know if you can add an AB line to that. We could try. Let's see what it does if we use AB line, which might work with these. So AB line, H equals 0. Nope, didn't like it. Or let's try, as you said here, using the geom H line, H equals this. And it got mad because that's not the right syntax. So really good questions right there. And that's why a lot of times I'll just click on this and I'll go to the help and I'll see how it's doing it. And I'll just copy paste from the help. And that will help me make sure I do the correct format. So even I have to double check because I'm like, okay, what does this one use again? It tells you have to tell what the y-intercept is. So it's very, very tricky to like remember every single syntax. You remember the ones you use a lot, but it's so, there's so many little things. So many little things. And I want to make the line thicker because we should be able to change the line. And I wish they showed that. There are ways to change the line with like, is it CEX? Let me try this. Or it's line width LWD. So I think it's LWD equals, that's line width. There we go. Look at that. That's line width. And I don't know why they don't show those things. So line width of 1.2. There's our line width. And I don't know if we go color. Can we do color here? Let's go to red. Oh, look at that. All these little improvements right here. I'll make this a little bit smaller. That's whatever you want. Once again, this is your own discretion where you want the line to be, how you want it to look. But you're just adding this line to it, the horizontal line with an intercept of 0, because that's where the line was originally at. The line width has been set to 0.8, and the color is red. So it's anything you want it to be. And I think it's line type. How do you do line type again? See, I always forget. Line type code in R. Line type code in R. It is LTY line type. And then 1. So 1 is the straight line probably. 2. There we go. So you can change the line type right here to different sorts of things. We probably just want the dashed line. But there's all different line types too. That could work too. But the default line type of 1 is probably what I would go for right there. What do you think, Jack, right here? Looking pretty good, right? But we have to change these to the residual value. That's on the y-axis. So this is the residual. And now we have over here the predicted value of miles per gallon. So we'll go MPG. Predicted value of miles per gallon. And you can see here the bend throughout the model, which would say at the lower portion, the points are above, towards the middle, the line is going through the center of the data. And then at the higher values, it is also showing the bend here at the end. Now, what's interesting is we could make the individual plots. You might just run those with the extra equals true on this. So here we are. Here's the individual plots, which really shows up in the weight, which is where we saw the bad p-value. Well, no, they're both bad. Horsepower is also bad. Yeah, horsepower's got a little bit of a bend there too. Interesting, this one is like a combined of the two. To make these individual plots, you would have to make individual models. Not against doing that. You might... see, I just don't love these little plots not looking so pretty right there. If you look at the difference between this plot we have right here and this plot we have right here, you know, this looks not so amazing, and this looks like a professional report you could see in a journal or something. So we want to go for these nice, clean outputs right here with great titles, great access titles, easy to read plots. And that's what we're working on here, is not just knowing the information, but presenting it well to the reader. The equal spread doesn't look to be a problem. I don't know how you'd add in the bands right here, but that is a much better normal quantile plot than the original one. And all we did was make a scatter plot, because that's what a normal quantile plot is, added the horizontal line, added our titles, and we're good to go. Also, trying to think what else. And we could look at some transformations about this, but we also might want to look at the variance inflation factor. And it's kind of decent. Like, yeah, it's kind of decent. 1.76 means the variance of the model has been inflated for these variables. Both of them are being inflated the same by about 1.766 as a factor. The standard errors of those variables has been inflated by about 1.33 because variance is standard error squared, so we get square root to find the standard error inflation. So with this right here, you wouldn't just want to present this information like this. Let's store it here as a table and K table. So cable extra and K table. Oh, nope. I always do this wrong. How do I always do this wrong, Jake? Jack, sorry, Jack, 100 points. I have a Jake and a Jack in 2 different classes, and now it's totally messing with my mind. So if you're watching this, now people know why I always make all these errors. Nidar? Why is that not showing up? I guess it shows when you knit. Why have I forgotten how to make a K table? Here we go. There it is. My gosh. Okay, there it is. So just need our table. There it is. Not so pretty yet, though. Not so pretty. Not good with the X on the top. It's not what we want. We want variance inflation for it. So we should be able to change the call names. Oh, column and row specification. Insert an image in the column? What? That's so interesting. Oh, here we go. Add header. I don't want to do that big of a header. So variable and variance inflation. Is it gonna do it? Oh my gosh, we did it. But oh, can it be a remove header? I just want to remove that X. Oh, yeah, I got an idea. Variance inflation. Okay. Well, we don't need the header now. So, yeah, not bad. Working with it and getting it the way you want it is the way to do it. So get this nice and neat. Make sure you have the right amount of decimals. Make sure it looks good. But we do have the variance inflation right there. I guess I can't really remove the name of the column, but the classic 2 right there, if you want to use it full width. Let's go true. What does that do? Oh my gosh, we don't want that. Just working around with these things the way you want to get it, the way to do it. Well, with that, I'm going to take a break right here. We'll be back more later on. But with that, it is time to say goodbye. Bye, everybody. Bye.